Here's our good friend, the Hadley cell. The Hadley cell, this is a cross-section, the side view with the surface. At the bottom, of course, the world is not flat, but it's a way I can showcase the Hadley cell. At the top, because it's a side view, that's going to be the top of our atmosphere, or sorry, our top of our troposphere, where all of our weather takes place, and that's the tropopause. What we have is the Hadley cell. Some characteristics of it is we have low pressure areas here in the center, causing warm, moist air to be pulled together, converging, and eventually it's going to converge, it's going to rise, condense, and fall back down as rain. So also associated with the equatorial low pressure trough is that dense rain belt. But we know that this air continues on as it makes its way towards the poles. But like I said beforehand, it doesn't make it all the way to the poles. And so what ends up happening is this air is essentially, it's dry. All of its moisture has been left behind in this equatorial low pressure trough. And so as it continues on, not only is it cool air, but it's dry air. The 30 degrees north and 30 degrees south also corresponds roughly with the subtropical high pressure. So it's actually the subtropical high pressure which kickstarts and causes the convergence that we find there along the equator at 0 degrees. And so this cell, this flow, is all called the Hadley cell. And so the Hadley cell is corresponding to the equatorial low pressure trough, that low pressure in the center, followed by the air continuing working its way towards the poles. It doesn't make it all the way, but then it descends and diverges. That makes sense. It's a high pressure in which we have that divergence coming back. And so it's essentially we have a cycle that flows here.